Effective use of the space domain is the new frontier of communication, and many effective solutions have been proposed for 6G. Shannon's theory has been applied with enormous success to analyze signals in the time domain. But, is the application of Shannon's theory in the space domain trivial? Or is it time to also consider the physics of the communication process? Let's consider communication systems that use time domain waveforms. Information is carried by a band-limited signal that can be represented by two Bt values sampled at the Nyquist rate. B is the bandwidth and T is the observation time. 2 Bt are the number of degrees of freedom of the waveform. Now, let us consider communication systems using space domain waveforms. Also in space it is possible to represent a waveform as a band-limited function having spatial bandwidth W, an extension of the observation domain xi. The number of degrees of freedom of the spatial waveform is 2W xi. There is a beautiful mathematical symmetry between communication in space and time. But the transmission of information also involves physics. Could physics break this symmetry? Let's go back to the time domain, and take a look at Shannon's theory, using the intuitive geometric approach based on packing spheres. Each possible waveform can be represented as a point in a 2Bt dimensional sphere whose radius depends on the transmitted power. The presence of noise can be modeled as a sphere of uncertainty around the point. Noise makes all waveforms represented by points falling within the same sphere of uncertainty, indistinguishable from each other. Consequently, only waveforms whose sphere of uncertainties do not overlap can carry distinguishable information. However, noise is a stochastic process and there is always a probability that the spheres overlap, giving a probability of communication error always greater than 0. However, when the value of 2Bt approaches infinity, this probability tends to 0. We can imagine that the soft spheres of uncertainty lose their stochastic nature and become hard spheres. The maximum amount of information that can be sent is equal to the maximum number of balls that we can pack, and the channel capacity is the logarithm of this amount per unit time. The key point of the procedure is to work in a functional space whose number of dimensions can be increased at will, in order to harden a sphere of uncertainty. Since the number of dimensions is 2Bt, it is possible to increase the observation time t, decreasing the overlap between the spheres at our will. Now, let's use space to convey information. The number of degrees of freedom of the spatial waveform in 2W xi. Physical space is infinite, so we should have no problem sending space to infinity and applying Shannon's theory. However, the physical constraints to which temporal waveforms and spatial waveforms are subject are different. Spatial waveforms are constrained by Maxwell's equations, which impose more severe restrictions to the set of spatial waveforms, compared to time waveforms. In particular, the spatial number of degrees of freedom is limited by the size of the antennas, and cannot be increased to infinity if the size of the antennas is bounded. Consequently, we cannot apply Shannon's theory. How to get around this problem? One possible solution is to use Kolmogorov's information theory, which directly considers hard spheres of uncertainty. Shannon capacity and Kolmogorov capacity are closely related cousins. While the former works in probabilistic spaces, the latter works in deterministic spaces. But when the probability tends to 1, the two approaches tend to converge. The maximum amount of information is given by the solution of the sphere packing problem involving hard spheres. Classical analysis of spacetime communication systems lacks connection with Maxwell's equations. However, this connection can hold some nice surprises, for example revealing a much faster increase in channel capacity by increasing the signal bandwidth. In the future, communication systems will get closer and closer to the limits imposed by physics. The introduction of physical constraints in the communication model allows to investigate the boundaries of the communication bit rate, without the risk of obtaining non-physical solutions. More information is available at the Google site Electromagnetics and Information. The topic is also discussed in this paper. Thank you for your attention.